So let's look at, this is the 2003 AP multiple choice AB calculus non-calculator portion. So for number one, we start off with binomial squared, and we're asked to find the derivative. So one thing is we can consider this as a chain rule problem. There's an outside portion and inside portion, and we take turns finding each of their derivatives. And the outside portion is the parentheses squared. The inside portion is the x cubed plus 1. And with the outside, we can apply power rule first. So we bring down the 2, we keep the parentheses, we subtract 1 from the exponent, so that's power rule for the outside portion, multiplied by the inside function's derivative. So x cubed becomes 3x squared, 1 goes to 0, and so the inside portion is 3x squared. We fill in the parentheses with the original function, no changes there. And if we multiply the outside portions together, we get 6x squared, parentheses x cubed plus 1, and that matches answer choice E. Another option is, because this is only binomial squared, we could FOIL, expand these terms out first. And if we do that, we're left with a trinomial, and we can just do power rule for each term. 6x to the 5th plus 6x squared, factor the GCF out, and that matches the answer choice as well. For number 2, we have a definite integral that also involves U substitution. So we have to just make sure that we don't make the mistake of evaluating the bounds first. Right, so this is the integrand. The integrand does not see the bounds. The bounds is for the antiderivative. So we got to put in the effort to figure out what the antiderivative is first, and then the final step, we work with the bounds. So this is a U substitution problem. This matches the rule of e to the u du. And if we're trying to match it up with this rule, then we should be able to identify our u value being the exponent. Our u value is negative 4x. So we find, we let that be our u value. We find the derivative, du dx equals negative 4. We cross multiply. We get negative 4 dx equals du. We want to solve for dx. And so we get dx equals du over negative 4. And our goal is to make these substitutions with the negative 4x and the dx. Right? So those are the pieces that we're trying to match up and replace. So negative 4x gets replaced with u, dx gets replaced with du over negative 4x, and we can push that negative 1/4 out in front, that coefficient, and once that coefficient comes out, we see that this matches perfectly with the rule that we want to apply. So integral of e to the u is just e to the u plus c, but this is a definite integral, so it's just going to be negative 1/4 e to the u. Now, we have the antiderivative. We have two options available to us. Either we convert the bounds, because the bounds right now, there's a mismatch in variables here. These are in terms of x, 0 and 1, but our antiderivative is in terms of u, so we have to make sure that there's a match between variables before we plug in. What we don't want to do is we don't want to evaluate this using 0 and 1, because if we're plugging 0 and 1 into this expression, then we're plugging x into a variable for u, and that doesn't make sense. So first option is we can convert the bounds. So the way we convert bounds is we can keep this antiderivative and convert those bounds to be in terms of u. So right now 0 is x. Our conversion is using this equation, u equals negative 4x. So if I replace 0 in for x, I'm going to get u equals 0. If I replace x in for 1, I get negative 4 times 1, which is negative 4. So our old bound has been converted to our bound in terms of u, and our upper bound in terms of x has been converted to in terms of u. Even though it does end up being a smaller value, don't worry about that. We've matched the old lower bound with the new lower bound, and we've matched the old upper bound with the new upper bound. So even if there's a mismatch, it's okay. Things will work out in the end. So we evaluate the bound, upper bound first. Upper bound gets plugged in for u, minus, then we evaluate the lower bound. 0 gets plugged in for u as well. Negative 1 over 4 e to the negative 4. Same thing as negative 1 over 4 e to the fourth. And e to the 0 power, same thing as 1. The two negatives become positive, so we get plus 1/4. And that matches with the answer choice of D. Okay. The other option is we can go ahead and convert all this to be in terms of x. If we do that, then we can rely on the original bounds provided in the problem, the 0 and the 1. So the second method is let's turn this u back in terms of x, and then we can evaluate the bounds using our original x values. So the original x value of 1 gets plugged in for x. We get negative 1 over 4 e to negative 4, minus plug in 0 in for x. We get plus 1/4, and we get the same answer. So either method is fine. What you don't want to do is use 0 and 1 for this antiderivative. Okay, for number 3, it says for x greater than or equal to 0, the horizontal line is an asymptote for the graph, a horizontal asymptote. Which of the following statements must be true? Now, one thing we need to make sure that we understand with horizontal asymptotes is that it's a little bit different than vertical asymptotes. Vertical asymptotes indicates that the graph is never going to be able to cross that value. But horizontal asymptotes, it only describes the end behavior. So it's okay for the graph to cross through or even have a point defined on that horizontal asymptote, because this is more of a guideline. This is telling us how the graph is behaving as we move towards infinity and negative infinity. So it's possible for a graph to be defined or exist on the horizontal asymptote. So that's something to keep in mind. So it's okay for f, which of the following must be true. F of 0 is equal to 2. That's not necessarily the case. The graph may not be defined at 0, 2. The graph does not equal to 2 for all x greater than or equal to 0. Now, this is not true because it's possible for a graph to be defined somewhere at y value of 2, even though there's a horizontal asymptote. F of 2 is undefined. That's not necessarily true, as we can see by this graph, this example graph here. The limit as x approaches 2 is equal to infinity. Well, if it's a horizontal asymptote, then the limit should be equal to 2. If it's infinity, then the graph will shoot up to positive infinity. And so that leaves us with option E. The limit as x approaches infinity is going to be equal to 2. Okay, number 4, we have a function with a numerator and denominator, a rational expression here. So if we want to find the derivative, looks like we can rely on quotient rule. So quotient rule, I identified the top as the f, the bottom as the g, and I'm just spelling out the parts that build my derivative using quotient rule. So f prime times g minus f g prime. The derivative of 3x plus 2 is 3, all over denominator squared. Careful that we don't simplify incorrectly, right? We can't cancel these 3x plus 2's out because this 3x plus 2 is attached to the minus sign. So we're going to just distribute through. Distribute, clean up the numerator. We get 6x plus 4 minus, distribute the 3 through. We get minus 6x minus 9. This cleans up to be 6x cancels out. We're left with 4 minus 9, which is negative 5. The denominator is 3x plus 2 quantity squared, and that matches answer choice D.